This is problem 13.123 on page 875. The coefficients of friction between the load and the flatbed trailer shown are static 40%, kinetic 35%. Knowing that the speed of the rig is 55 miles an hour, determine the shortest time in which the rig can be brought to a stop if the load is not to shift. Okay. There's a poor rendition of the rig. Something like that. And the trailer. And there's a load on the trailer. Static coefficient of friction, 40%. Kinetic coefficient of friction, 35%. The truck is moving at 55 miles per hour, and we'd like to know the shortest time where we can go to a final speed of 0. So this is the velocity, velocity in state 1, velocity in state 2 is 0. And so what's the minimum time for that speed change to occur without the load shifting? All right. Well, let's think about what we mean by some of these things. Well, let's start off with 55 miles an hour. Let's convert that to feet per second. So multiply by 5280, divide by 3600.
80.67.
Thanks. 80.67 feet per second. Now, we know what section this is in, so we can cheat just a little bit and write down the equation, which is the conservation of momentum. That's really what it is. mv1 plus the integral of f dt from state 1 to state 2 equals mv2. We're going to take this system from an initial velocity of 80.67 feet per second to 0. So we know this is 0, but we don't know how much mass there is. They didn't tell us. Well, that's okay. We have to choose a system, however. Do we want to take the big rig and the package itself? I don't think so, because here's the thing. We need to consider forces external to the system. If we take the truck and the package as a system, what forces act externally to it? Well, friction between the wheels and the ground. So we might have to consider what happens when we have static versus kinetic friction between the wheels and the ground. But that's not the question. The question is not will the wheels of the truck slide. The question is how do we keep the package from sliding? So really our system, let me draw our system in blue. Our system is just this. You see, we're interested in forces. All these forces had better be external to the system. What forces are there? Well, there's a normal force, there's a weight force, and there's a friction force. It's the friction force that decelerates the load. Yeah, okay, in the real world, we don't just set loads on the backs of trailers and hope they'll stay in place. We tie them down. You know what tie-down straps are for? Increase the friction. Have you ever noticed that they don't usually tie down things, well, some do, but they don't often tie down loads in this direction. They put the straps in this direction. They increase the effective weight. What that does is clamp the package or the pallet or whatever it is against the bed so that you can increase the frictional force. It's still the frictional force that moves or decelerates and accelerates the load. So let me ask you a question. Does the weight or the normal force act during the time when we're decelerating the package? Yes, but number one, they're not in the direction we're interested in. Remember that actually this is a vector equation, and the only direction of motion that we're going to change is that direction. So there's two reasons we want to include the normal and the weight force. Number one is that the normal and weight force are not in the correct direction. We don't care about the vertical direction, right? Number two, they balance out each other, right? So their effect over time, that's the reason it doesn't move over time as we decelerate, because those two forces balance. But we're interested in this direction. Not only that, but it's possible that this frictional force will be much larger than the normal force and the weight force. Well, that's not really possible, is it? Because the friction force will be equal to a fraction of the normal force. But more importantly, the normal and weight force are not in the direction of interest, so that's why they don't appear in the equation. In fact, really the equation is going to be an x direction equation, maybe something like this. Let's put x positive to the left y positive up. In that case, it would be mvx1 plus whatever forces act in the horizontal direction over time, give us a zero velocity in the x direction. Okay? Now, what force acts in the x direction? Well, it's the friction, but it actually acts in the negative direction. As a matter of fact, the only force that acts that changes the velocity or changes the momentum over time is friction, and the friction would be equal to, well, we have to be careful. The thing that goes in here, because this is a direction equation, will be negative mu(m). Why did I put that negative sign on there? Because this is a vector, right? It's talking about a direction. Positive is that way. The momentum is positive in that direction. The impulse is going to be in the negative direction because the force that causes that impulse is in the negative direction. Does that make sense? So we'll write mvx in first state plus integral from state 1 to 2 of negative mu n, but n is just weight, w, dt equals 0. But weight, what is weight? It's mg, isn't it? Now, what mass are we talking about? I see the mass of the truck and the mass of the package. What mass are we talking about here? Mass of the package. Why? Because this is a momentum equation that only deals with the package. How do I know that? Because the only external force that I considered was the force of friction. That's a force on this package, or pallet, or whatever the load may be. You can say, well, equal and opposite friction acts on the truck. That's true. But so does friction from the wheels or from the road, between the wheels of the road. We're not talking about the truck. We're talking about the pallet or the load or whatever it's called. Okay? So you notice that they've set this up and not told us the mass of the pallet simply because it cancels. So let me pull out negative mu g. Notice I'm canceling the mass. Integral 1 to 2 dt. I pulled out everything, right? Negative mu g, all that came out. They were all constants, equals 0. So what is the integral of dt? Simple, t. It's the amount of time to go from state 1 to state 2. And that's what we want to know. How much time does it take? Well, let's see. Vx1 equals mu g t from 1 to 2. So the time to go from state 1 to state 2 equals Vx1 divided by mu g. So that time, that minimum time, why minimum time? Well, we're assuming we're going to apply the maximum frictional force possible so that it doesn't slip. So if it's not going to slip, what does that mean? Do we need to use mu s or mu k? Yes. Now there is a nuance here that I'm skipping over, but I'll talk to you about it in a second. So Vx1, 80.67 feet per second divided by 0.4, 40%, the static coefficient, times the weight, well, not the weight, but g, 32.2 feet per second squared, gives us how many seconds it takes to bring this package to rest.
6.26.
Thank you. So that's how long it's going to take to go to rest if we don't want this package to slip or this load to slip. What was the nuance? Well, the frictional force here is a maximum frictional force, isn't it? Notice that I made a big assumption here. I assumed that friction force was constant. You see, it's possible that the driver would slam on the brakes so hard that that friction force would be overcome, it would break loose, and we'd have a kinetic situation, right? But if that happened, then the package would have slipped. On the other hand, it's also possible that the driver would have just barely touched the brake pedal and would not have stopped in that time, would have stopped in a longer time by generating a lower friction force. It's also possible, but they asked for the minimum time, so I assumed that friction was at its maximum, was on the verge of slipping the entire stop. Okay? Probably not the best assumption, but there it is. I don't know that the driver could actually sense how well, the package was tied down and not over brake. How much friction force would you need to make sure that the package never slips by comparison with a truck? You'd want to make sure you had a friction coefficient here larger than what friction coefficient was possible between the roadway and the tires, right? Because if you lock up the brakes hard enough, either that's going to slip or that's going to slip, or maybe both, right? But ideally, you tie this down hard enough so that by the time the wheels slip, well, it's too late anyway at that point. You don't really need to tie down the load any harder than that, because it's not going to slip. Now, there's probably other things to consider, maybe bouncing and vibration that would mean you actually need a higher clamping load than what I've said, but just theoretically, the maximum friction you would need would be equal to the friction coefficient between the tires and the road. Any questions?